3 unequal piles, 48 matchsticks in total. You are told nothing about how many matchsticks are in each pile. 3 operations are performed in sequence. First, transfer from pile 1 to pile 2, as many as pile 2 already contains. Then, transfer from pile 2 to pile 3, as many as pile 3 already contains. Then, transfer from pile 3 back to pile 1, as many as pile 1 currently holds. After all 3 operations, every pile contains the same number of matchsticks. How many were in each pile at the very start? Pause and try it. The obvious approach: guess some starting numbers and simulate the operations forward. Say pile 1 has 20, pile 2 has 16, pile 3 has 12. That totals 48. Apply operation 1. Transfer from pile 1 to pile 2 as many as pile 2 has. Pile 2 has 16, so move 16 from pile 1. Pile 1 becomes 4. Pile 2 becomes 32. Already the numbers look wrong. After 3 operations from this start, the piles will not equalize at 16. Try different starting numbers. Eventually you will find one that works, but it is slow, tedious, and gives you no insight into why the answer is what it is. There is a principle hidden inside this problem that makes it immediate. One step rather than dozens. The principle is this: start from the end, not the beginning. We know exactly what the final state looks like. After all 3 operations, every pile is equal. Total is 48, so every pile is 16. Start there. Work backwards. State after all operations: pile 1 16, pile 2 16, pile 3 16. Now undo operation 3. Operation 3 transferred from pile 3 to pile 1, as many as pile 1 held at that moment. Pile 1 is now 16. For it to have doubled, it must have been 8 just before operation 3. Pile 3 gave it 8, so pile 3 must have held 24 just before operation 3. State before operation 3: pile 1 8, pile 2 16, pile 3 24. Total still 48. Now undo operation 2. Operation 2 transferred from pile 2 to pile 3, as many as pile 3 held at that moment. Pile 3 is now 24. For it to have doubled, it must have been 12 just before operation 2. Pile 2 gave it 12, so pile 2 must have held 28 just before operation 2. State before operation 2: pile 1 8, pile 2 28, pile 3 12. Total still 48. Now undo operation 1. Operation 1 transferred from pile 1 to pile 2, as many as pile 2 held at that moment. Pile 2 is now 28. For it to have doubled, it must have been 14 just before operation 1. Pile 1 gave it 14, so pile 1 must have held 22 just before operation 1. State before operation 1, the original starting state: pile 1 22, pile 2 14, pile 3 12. Verify. 22 plus 14 plus 12 equals 48. Confirmed. That is the complete backward reasoning chain. 3 undos, 3 lines of arithmetic. Done. Let us run the operations forward from 22, 14, 12 to confirm. Operation 1. Pile 1 gives pile 2 as many as pile 2 has. Pile 2 has 14. Transfer 14 from pile 1. Pile 1, 22 minus 14 equals 8. Pile 2, 14 plus 14 equals 28. Pile 3. Unchanged at 12. Operation 2. Pile 2 gives pile 3 as many as pile 3 has. Pile 3 has 12. Transfer 12 from pile 2. Pile 2. 28 minus 12 equals 16. Pile 3, 12 plus 12 equals 24. Pile 1. Unchanged at 8. Operation 3. Pile 3 gives pile 1 as many as pile 1 has. Pile 1 has 8. Transfer 8 from pile 3. Pile 3. 24 minus 8 equals 16. Pile 1. 8 plus 8 equals 16. Pile 2. Unchanged at 16. Final state 16, 16, 16. Confirmed. The backward reasoning principle generalizes. Whenever you know the end state of a reversible process, you can find the start by undoing each step in reverse order. This is exactly the logic behind solving equations. Substitute and trace back. The original pile sizes were pile 122, pile 214, pile 312. The principle? Backward reasoning. When the final state is known, undo each operation in reverse order. Each doubling undoes to a halving. What if the final equal state were 20 each? 3 piles of 20, 60 total. Find the original pile sizes. Post your working. If you enjoyed unraveling this mathematical mystery with us, hit the like button and subscribe for more deep dives into math and science. Let us know in the comments what other puzzles we should explore next. Thanks for watching.